Hello. Today we're going to be looking at section 3.4, which covers different rules for logarithms. So let's go ahead and take a look at our first rule. We have the inverse rules, and these state that the exponential function and the logarithmic function are inverses of each other, and this shows how they cancel each other out. Right, so we learned that they were inverses in 4.2 when we did we found the inverse of different functions, and the inverse of an exponential function ended up being logarithmic, and vice versa. So this shows us in what way these actually cancel each other out. So a base a exponent will cancel out with a log base a as long as that log base a is in the exponent, right? So it's a little bit weird, but we have a base a here for the exponent, and in the exponent we have log base a. So it's important that the bases are the same. And with that being the case, these literally cancel each other out. The log base a cancels out with the base a exponent, and all we're left with is x, which just falls to the ground, right? So I know it's kind of stuck in the exponent up here, but when those cancel out, it has nothing to hold on to, drops to the ground. The reverse direction, in order for a log base a to cancel out with a base a exponent, that exponent needs to be inside the logarithm. So again, here what's going to happen is the base a of the logarithm cancels out with the base a of the exponent, and then all that's left is x, and so that's going to be our answer there. So this shows how logarithms and exponents cancel each other out. So let's take a look at an example. So these will be the easiest problems on the homework by far. So here we have a base 10 exponent. This is log base 10, right? It's not written there, so we have to assume it's a 10, and so they will cancel each other out. This 10 cancels out with this log base 10, and the answer here is just going to be whatever was inside the logarithm, which is square root of b. That's all there is to that. Same thing's happening here. Natural log is log base e. The base of the exponent inside the logarithm is also base e, and so they will cancel each other out. This logarithm cancels out with the base of this exponent, and so our final answer here, all that's left over, is 3x. All right, let's take a look at the next rule. We have the product rule. So the way this works is a little bit weird, but we have log base a of m times n. So notice we are multiplying inside the logarithm. That's why it's called the product rule, because we're multiplying there. But the way that can be rewritten is a little bit bizarre. You can split this up and put each factor here, the m and the n, inside of their own logarithms. So we can split it up and write each thing inside of its own logarithm. But then what we do with these individual logarithms is we add the logarithms together. So the fact that they're being multiplied here, leads me to add the individual logarithms together over here. So that multiplication, it doesn't really transform into an addition, but that's what it leads to with the individual logarithms. The reason it behaves in this way is because when you multiply two things together, like we're doing here, you would do what with the exponents? You would add the exponents, right? So if these things had exponents on them and the bases were the same, you would add those exponents together, right? When two things are being multiplied, so when you multiply, the exponents are added. All right. And so that is why we are adding the logarithms, because remember, we studied logarithms in 4.2, and we talked about that logarithms are exponents. That's what they're representing, and so that's what dictates their behavior. And so because the logarithms here are representing what those exponents are in this situation when these are being multiplied, those exponents need to be added together. So I know it's sort of an abstract explanation for why the rule works the way it does, but that is the basis of it. When two things are being multiplied, that's when you would add the exponents. Like for example, x squared times x to the third power, right? If you multiply those two things together, you're adding the exponents together. All right, so that's why the logarithms are being added together. Okay. So let's take a look at some examples. So here we are adding these two logarithms here. I'm sorry, I'm pausing because I was paranoid that my mic wasn't on, but I think it is. So I'm going to keep going. I'd hate to talk for 50 minutes and then find out my mic wasn't on the whole time. So I hope it's on. So I'm adding these two logarithms together. So what I can do using the rule that we were just looking at on the previous screen in the reverse direction, right? We're starting with something that looks like this, two logarithms that are being added together. We can rewrite that as a single logarithm by multiplying these two things together inside of that single logarithm, right? So we're going to be working backwards here, starting with the two logarithms being added. We're going to rewrite it as a single logarithm, but we will multiply those two things together. All right, so I'm sorry I'm repeating myself, but I just want to make sure everybody caught that. All right, so I'm going to rewrite this as a single logarithm. The base of the log will stay the same, so it'll still be log base 5. And inside of that single logarithm, I am going to multiply these two things together. I'll take the x plus 6, and I'm going to multiply it to x plus 7. Right. So because these are being added, that's why I am choosing to multiply these two things together. Right. And that's the answer, but I assume that MathExcel, when it says simplify, it's going to want you to FOIL this out and combine like terms. So let's go ahead and FOIL. So we get x times x, which is x squared, x times 7, which is 7x, 6 times x, which is 6x, and 6 times 7, which is 42. Right. Then we'll combine these two terms together, so we get x squared plus 13x plus 42, and that'll be inside of this single logarithm, log base 5. All right. And the reason I'm switching from brackets to parentheses is I use brackets up here so it doesn't blend in with the parentheses that I'm already using inside the logarithm. But once those have been dealt with and there's no more parentheses inside the logarithm, I can just go back to using parentheses for the logarithm itself. All right, so this one is the reverse direction. We have a single logarithm already with two things being multiplied together. They want us to rewrite it as separate logarithms. So what we're going to do is we're going to split these up. Each factor is going to get its own logarithm. So the c will get to have its own logarithm, log base 8, and d will get to have its own logarithm. And what we're going to do with these two logarithms is we are going to add them together. Right? If they're being multiplied inside the logarithm, we want to add the separate logarithms to one another. And so this would be the result for this one. All right. Next rule is called the quotient rule. So here we have log base a, and this time we are dividing. So I think a lot of students can kind of guess what's going to happen here. If you're multiplying two things together inside of a single logarithm, you would add the individual logarithms together. So if you are dividing two things inside of a single logarithm, that is going to lead to us subtracting the individual logarithms. Now, when you're subtracting, it does make a difference the order that you subtract in, so it's very important that whatever's in the numerator goes into the positive logarithm, and whatever's in the denominator goes into the negative logarithm, right? This one's the negative one. That's where the denominator needs to go, right? So again, we could take a single logarithm, split it up into separate logarithms here by subtracting when the two things are being divided over here. It also works in reverse. If we have two logarithms that we are subtracting from one another, we can collapse those into a single logarithm by dividing those two things. The positive one goes on top, the negative one goes on the bottom. All right, so let's take a look at an example. So here we're subtracting these two logarithms. We want to rewrite this as a single logarithm. And so I'm going to write this as a single natural log. And because I'm subtracting these two logarithms, I'm going to divide these inside of my single logarithm. The thing from the positive logarithm is going to go on top, so x to the 5th power goes on top. The thing from the negative logarithm goes on the bottom. So I'll divide those two things. Sorry, let me try that parentheses again. And then I'm going to simplify, right? And so to divide, since these have the same base, we can divide these by subtracting the exponents, which again is why this rule works the way that it does, right? The reason I didn't explain it like I did on the first one, but the reason this rule works the way it does is because when you're dividing two things like, x to the 5th power divided by x to the 2nd power, you subtract the exponents. That is why we are subtracting the logarithms, because the logarithms are representing the exponents there. All right, and so we end up getting this. Right. Natural log of x squared. The reverse direction, we have a single logarithm here. We want to rewrite this as separate logarithms. So each factor will have its own logarithm. So d will have its own logarithm, and 10 is going to have its own logarithm. But this time, since these were being divided, we are going to subtract these logarithms. Now, I'm not sure how Math Excel is going to feel about us leaving the answer like this, because there's one thing we could do to simplify, but you may not always have this opportunity. But log, this is base 10, right? The base isn't written there, so it means it's base 10. And we have a 10 inside of this logarithm here. So log base 10 of 10, if you remember, is equal to 1. Right? How many powers of 10 does it take to equal 10? The answer is 1. And so that could be simplified in that way. This can't be simplified at all, so we'll leave it the way it is. Let me rewrite those things. I didn't do a very good job there. So there we go. So log base 10 of d minus 1 would be a better way to write that. Math Excel may not care either way. I don't know. You could take your chances leaving it like this, but hopefully it would accept it if you simplify it. All right. So that's the quotient rule. So here are a couple more challenging examples using both rules actually. So this example uses the quotient rule. So we have natural log, we have x minus 9 on top, we have x on the bottom. It wants me to write these as separate logarithms, so each factor is going to have its own logarithm. Now I say factor here because x minus 9, you might say, well, there's an x and there's a 9, but those are not factors, right? They're being subtracted, they're not being multiplied to each other. So we can only split it up into separate logarithms if they're being multiplied or divided, not if they're being added or subtracted, right? So this x minus 9 has to stay together. We can't split it up. So x minus 9 will go inside of its own logarithm, and then the x from the denominator will go inside of its own logarithm. And what will I do with these two logarithms? Because I'm dividing here, I'm going to subtract. I will subtract these two logarithms. All right. And that's as far as we can take it. And again, a lot of students will make the mistake of thinking, well, this x and this 9, we have to split that up. You can't split up something inside of a logarithm if they're being added or subtracted inside of that logarithm, right? Which is actually the stumbling block we have here. So this, the way it's written, cannot be split up. It's not being multiplied, it's not being divided. These two things are being subtracted. So these cannot be split up into separate logarithms initially. But what we can do with x squared minus 100 is we can factor it, right? And so that factors as x plus 10 times x minus 10. Right? And so we want to take the log of that. Now I'm going to do the thing I did earlier. I'm going to switch to, instead of using parentheses around this thing, because I have these parentheses here, just to make it easier to read, I'll put brackets around the whole thing. Right? But I'm taking log base 10 of x plus 10 times x minus 10. Now they're factors, right? Now they are being multiplied together, so these can be split up and placed in their own separate logarithms. And so I'll put the x plus 10 inside of one logarithm. I'll put the x minus 10 inside of another logarithm. And what am I going to do with these two logarithms this time? I am going to add them together because they were being multiplied here. So these logarithms should be added to one another. All right. So that one's a little more complicated. We had to set things up first before we could apply the rule that we just learned. All right. Now this is what I thought I was about to talk about a moment ago. This is the power rule, which is actually one of my favorite rules for logarithms. It's just kind of a neat rule that, I don't know, allows you to do a neat thing, which is to take the exponent inside of a logarithm, right? So we have log base a of m to the power of n. And so if everything inside your logarithm is being raised to some power, you can bring that power outside the logarithm by multiplying it down in front. So I think it's just a neat rule. So you can take an exponent that's stuck in the air and you can bring it down to ground level by multiplying it in front of the logarithm. Right? So this becomes n times log base a of m. Right? So that's called the power rule. Also works in reverse, right? So if you have something that looks like this, you can bring this power of n back inside the logarithm and it becomes an exponent, right? So you can bring this, I called it a power, it becomes a power, but you know, it's a factor here being multiplied to the logarithm. That can be brought back inside the logarithm and it becomes an exponent when you do that. So it's kind of a neat rule. It works both directions. All right, so here we want to apply that power rule, but the rule only works if you have an exponent. And this is not an exponent, it's a radical. However, radicals can be written in exponential form. So I'm going to rewrite this fourth root as 10 to the, does anybody know what this power should be? it should be to the 1/4 power. Right? So we don't see this very often, but it's going to come up a couple of times here and there in chapter 4. Right? So a cube root is a 1/3 power, a square root is a 1/2 power. That's just a handy thing to remember because every once in a while it comes up. And so we're going to rewrite this 4th root as a 1/4 power. And now that we have it written as an exponent, we can apply the power rule and bring the 1/4 as an exponent, multiply it down in front of the logarithm. And so this becomes 1/4 times the natural log of 10. And that's what they wanted us to do with this problem. And that's expressing it as a product because these two things are being multiplied together. All right. And so that's how the power rule works. You need an exponent, and then once you have the exponent there, it can be multiplied down in front of that logarithm. Okay, so this one, here's where things get a little bit more complicated. So they're going to start piling more things inside of these logarithms and asking us to split it up into separate logarithms, and vice versa. They're going to start giving us more than just a couple of logarithms, like they'll give us 3 or 4 that we have to compile back into a single logarithm. So things are going to get a little more complicated here. So here's the shortcut. I'm just going to jump right into the shortcut here. You want to, each factor from the numerator and the denominator gets to go inside of its own logarithm. So here we have just 11 on top, so that will go inside of its own logarithm. So we'll have log base 2 of 11. Here you want to be careful about this. There are 2 factors here, 4 times y, right? And so those are 2 different factors. They get separated as well. So each one of those will go inside of its own logarithm. So we'll have log base 2 of just 4 and log base 2 of just y. So every factor from both the top and the bottom of the fraction gets split up. And then the way it ends up working out, and this is, like I said, it's a shortcut to just jump to the answer. If the factor came from the numerator, then your logarithm should be positive. Right? And so this factor of 11 came from the numerator, so this logarithm will stay positive. If the factor came from the denominator, that logarithm, since you're dividing by those factors, those logarithms should be negative. So this 4 came from the denominator, so this should be a negative logarithm. We should be subtracting it. And this y, also a factor from the denominator, so we'll make this logarithm negative as well. Right? So if it comes from the numerator, make it positive. If it comes from the denominator, make it negative. Make the logarithm negative. And that's it. That's splitting it up. Now we have this same thing come up here that we did a moment ago with log base 10. This logarithm can actually be simplified to a nice simple number, and so it's a good idea to do that. Now, if it's on the test, I probably won't be too picky about it because I'm just happy if you were able to get this part right. But Math Excel may want us to take these things as far as we can. So log base 2 of 4, how many powers of 2 does it take to equal 4? Well, there's an easy answer for that. It's 2, right? And so we should simplify that. So it's nice if you do that. If you don't on the test, I may take off like half a point, but it won't be that big of a deal. I'm not going to be too critical about that because the main topic of this problem is just, can you split up the logarithm into separate logarithms? If you're able to do that, that's what I'm trying to test you on. All right. Okay. So that is the answer for that one. Okay, like I said, so these get a little bit crazy. Again, we have a radical here, which we can't do much with in radical form, so we want to convert it to exponential form, because if it's an exponent, we can actually do more with that. All right, so I'm going to rewrite this problem, natural log. I'm going to rewrite the 5th root as a 1/5 power. So we're going to have x and y both, because those are both inside the radical, they both get raised to the 1/5 power. And on the bottom, this was already written in exponential form for us, thankfully. So it's going to be t to the 5/3 power. And so that should be a little bit bigger here. All right. Now this exponent applies to both the x and the y. So what we can do is we can distribute it or apply it to each factor separately. So we'll have natural log. We'll have x to the 1/5 power, y to the 1/5 power over t to the 5/3 power. All right. So that's just kind of getting things set up for us to be able to apply the rules that we're learning from this section. So I'm going to follow the same shortcut that I used on the previous example. Each factor from the numerator and the denominator is going to get split up and be placed inside of its own logarithm. So we have x as a factor in the numerator up here. We have y as another factor because these are being multiplied together. And then we have t from the denominator. So we're going to put each of these inside of their own separate logarithm without their exponents. We're going to deal with the exponents separately. So just x, just y, and just t. Right? So we'll have x gets to go inside of its own logarithm, y gets to go inside of its own logarithm, and t gets to go inside of its own logarithm. Now what we do with the exponents is we use the power rule, and remember we can take exponents and multiply them down in front of their respective logarithms. Now we can't do that here because there's just too many different exponents and too many different bases, but once these get split up into their separate logarithms, that power of 1/5 technically does follow the x, but then we're going to take that power of 1/5 and use the power rule to put it down in front of the logarithm. So all of these exponents that you have here, ultimately, this is a shortcut, they ultimately just end up in front of the logarithms of their respective bases, right? So this power of 1/5 is going to end up in front of the logarithm with x. So I'll have a 1/5 power here multiplied down in front of that logarithm. This power of 1/5 goes in front of the logarithm containing y, and this power of 5/3 goes in front of the logarithm containing t. Right, so take these exponents, multiply them in front of their respective logarithms. That's what you ultimately want to end up doing with that. And then, just like we did in the last example, if the factor is from a numerator, you keep that logarithm positive, right? X is from the numerator, so this logarithm is going to stay positive. Y is also from the numerator, so this logarithm should stay positive, so I'll put a plus sign there. This factor came from the denominator, so this logarithm needs to be negative. And that's the quickest way to get to the answer. Now you could do it one step at a time. You could do, these are divided, so you do the quotient rule and you'd start with just doing that first. And then because these two things are being multiplied, you would then apply the product rule to that part of it and split it up. And then you could do the power rule. And you could do this problem in like 4 or 5 steps, but this just jumps you right to the answer if you set it up like this. Same thing here, right? We could do this piecewise, one step at a time, by taking the numbers, making them exponents inside the logarithms, then applying, taking 2 logs at a time and either multiplying or dividing depending on if it's added or subtracted. But we're just going to do it all at once and just jump to the final answer. So this, we want to write this whole thing as one logarithm. So we're going to collapse all this down to a single logarithm. The base of that logarithm is going to stay the same. It'll be base p. And just going backwards, what we're going to do is look at the different things inside of each of these logarithms. If it comes from a positive logarithm, then that factor needs to go in the numerator. And if it comes from a negative logarithm, then that factor needs to go into the denominator, right? So s is from a positive logarithm, so s will go in the numerator. T is from a positive logarithm, right? It's positive here, so t will also go in the numerator. Y is from a negative logarithm, so y should go in the denominator. And a is from a negative logarithm, and so a should go in the denominator. And it just multiplies to whatever's already there, right? And then we go back and we grab the numbers that are in front of these logarithms, and those will end up in the final answer as exponents on each of these factors. So the number in front of the logarithm with s becomes an exponent on the s, right? So 3 will become an exponent on s. T, the exponent for that would be 1/2, right? Because the number in front of that logarithm is 1/2, so that would become the exponent on t. For y, the number in front of that logarithm is 3/2. Now you might say, wait, isn't it negative 3/2? But the negative sign is why we placed it in the denominator. So we don't need to use it again as part of our exponent. Just take the number, 3/2, that becomes the exponent on the y. And same thing here, don't worry about the negative sign, we already processed that. Just take the 3 and make that the exponent on the a. All right, and that's it. That's how you collapse it down into a single logarithm. All right. So I know it seems kind of a daunting task, but if you practice that a couple of times, you'll get the hang of it. All right, so solving exponential equations. So this is another technique. Now I put technique number 2 here, but I think I already used technique number 2 in 4.2, which was to do the loop, right? So I really probably should change this, and so I'll have to do this for the future classes that I teach. But this should be technique number 3. So the 3 techniques that we are dealing with here is the first way you try to solve an exponential equation is to get both sides to have the same base. If you can make that happen, that's the easiest way to solve it. That's the way you want to do it. If that doesn't work, Another way of solving an exponential equation is to convert it to logarithmic form. So I said you do the loop thing, but that's for logarithmic equations. But what you could do with an exponential equation is rewrite it in logarithmic form, and that would allow you to solve the equation. This is a slightly different version of that technique. So instead of rewriting it in logarithmic form, what you could do is apply a logarithm, and you could use either one of these, log base 10 or natural log, to both sides of the equation. And then the power rule allows you to take the exponent and bring it down to the ground where you can actually solve for that variable. So it's using logarithms, but it's not converting it directly to logarithmic form. It's applying a logarithm to both sides. The reason we choose log base 10 or natural log is because these buttons are on everybody's calculator, right? Everybody has a log base 10 button on their calculator. Everybody has a natural log button. So this would allow us, once we solve it for x, to plug this into our calculator to get approximate solutions instead of having to leave it in logarithmic form. So that's kind of what makes the difference there. If you want the exact answer, you should use technique number 2, which is convert it directly to logarithmic form. If you want an approximate answer that you can plug into your calculator, you should use this technique, technique number 3. Use a logarithm whose base we can plug into our calculator to get our estimate that way. So let's apply that technique here. Let's review the previous technique. So one way we could solve this equation is convert it to logarithmic form. So the way that worked is you would start by writing log. The base of the exponent becomes the base of the log. And this is the way I like to do it. And I know in class this semester anyways, a lot of you were able to tell me right away what goes here, but that's hard for me. I don't know why. So I have to do it this way. The logarithm should equal the exponent. So my exponent is x. That's what logarithms equal. Logarithms equal exponents. So by elimination, 7 is what has to go inside the logarithm. And that's solved for x. So this would be the solution to the equation. But many of us are not going to be able to type log base 2 into our calculator. So while this gives us an exact solution, which is what we want sometimes, that is not what we want here, right? We want the approximate solution. All right, so let me, actually I'm just going to do that. I want to try to rewrite that C again. All right, that's going to bug me. All right, so exact. This time we want the approximate solution. We want to be able to plug it into our calculator and get a decimal for it. And so that might not work for us if we don't have that option on our calculator to do base 2, which, like I said, many of us don't. So what we can do is use this technique that we just talked about on the previous screen. Apply a log base 10 to both sides of the equation. So let's do this a different way. So this was technique number 2 that we learned in 4.2. Let's apply technique number 3 instead so we can plug it into our calculator. So we have 2 to the x power equals 7. I'm going to leave a little space here. I'm going to apply a log base 10 to both sides of this equation. Right, it's balanced because I'm doing the same thing to both sides of the equation. And then we can use the power rule that we learned in this section, which tells me the exponent here inside the logarithm can be multiplied down in front of the logarithm. So I can take the x, which is stuck in the air, it's stuck in the exponent, I can bring it down to the ground, multiply it in front of the logarithm. So then we have x times log base 10 of 2 equals log base 10 of 7. Now I can solve this for x by dividing this log base 10 of 2 to the other side. Now I know in class in section 4.2, I talked about you can't divide by an empty logarithm to solve an equation, but this is not an empty logarithm, right? This logarithm has a number attached to it, and so this is a valid division. We're dividing by a number here. Log base 10 of 2 is some decimal number that we're dividing by. So this is perfectly fine. That cancels out the log base 10 of 2's over here, and so I'll get x equals log base 10 of 7 divided by log base 10 of 2. Now this is still an exact solution. It's a little more complicated than what we got over here, but it's the same solution. Right? This answer is really the same as this answer, even though this looks a little more complicated. But this we can plug into our calculator and get a decimal solution. So I can say x approximately is going to equal, so I need a calculator, which I did not come prepared to this video to do that. So let me find my calculator. I might kind of, the audio might go out for a second as I go look, so just give me a second. Okay, I apologize for the break in the video there. So I have a calculator now, so we'll do log base 10 of 7 divided by log base 10 of 2. And so my calculator tells me that is approximately equal to 2.8074 if you round to 4 decimal places, which seems to be Math Excel's preference. I know it's not on the screen, but my recollection on that is that that's what they like you to do every time. So 4 decimal places. So this would be our approximate solution. Oops, I don't know why it went like that. Okay, let's try to do that again. Rectangle. All right, I almost did it again. All right, so this would be the approximate solution. Okay, so you have to pay attention to the directions. If the directions say, solve this equation, give the exact solution, you want to leave it in logarithmic form. So the quickest way to do that is just convert it directly to a logarithm, and you don't care what the base is because you're just going to leave it as a logarithm. But if the directions say, approximate the solution, you're going to have to use this technique, so you can use a log base 10 so you can plug it into your calculator. All right, so let's try the same thing on this one. We'll apply, and again, it says round to 4 decimal places, so it wants the approximate solution. We will apply a log base 10 to both sides of this equation. And we'll use a power rule. We can bring this exponent, 4x, multiply it down in front of the logarithm. So we'll get 4x times log base 10 of 1.83 equals log base 10 of 3. And then to solve it for x, we will divide by a couple things here, because I want to get x by itself. So I'm definitely going to divide by this logarithm, because I want to get rid of that. So I'll get log of 1.83. But I also want to get rid of this 4, which is also being multiplied to the x. So while I'm at it, I'm just going to go ahead and divide by 4 as well. Might as well do both of them at the same time. So I'll do the same thing over here. 4 log base 10 of 1.83. All right. So the 4's cancel out, the logarithms cancel out, and we end up getting x equals log base 10 of 3 divided by 4 times log base 10. Sorry about that. Let's try that again. Wow, didn't realize I made that many marks there. Okay, log base 10 of 1.83. Okay, so now that's still exact, right? That's still an exact solution, but we want the approximate solution here, so we will plug this into our calculator. Now you need to be careful plugging this into your calculator, because if you just type in log base 10 of 3 divided by 4 log base 10 of 1.83, just exactly how I just stated it without anything additional, you won't get the right answer, at least for the calculator I'm using, because it's going to follow the order of operation. And since this is all multiplication and division here, it's going to treat those from left to right. So it's going to say, okay, you have log base 10 of 3, then it's going to divide that by 4, because that's what you have in your calculator, divided by 4. But then the next thing here is it's times log base 10 of 1.83. And which we don't want it to multiply by log base 10 of 1.83. We want that to also be part of the division. And so in order for our calculator to process this correctly, we need to use parentheses around this denominator. So on paper, we don't really need parentheses here because it's clear what we're dividing by. But the calculator is going to be confused unless you put parentheses around the denominator, right? And so I'm going to go back and do that. So I'll put parentheses around the denominator because I kind of skipped over it as I was talking about it. And what you should come up with is this answer. So if this is not what you're getting, you might want to make sure you double check you're typing it in the calculator correctly. You get 0.4545, right, if you round to 4 decimal places, right? So it's really a 4 here, but we're going to round that up because of the 8. All right, so you might want to make sure, if you have a calculator handy, go ahead and try the same thing in your own calculator. Make sure you're plugging it in correctly, that you're getting the same answer that I have here. All right. So I think this is the last topic, right? So we're almost done. Change of base formula. So what we just witnessed on the previous screen here, and we just talked about this. This log base 2 of 7, which is exact, is equivalent to this, log base 10 of 7 divided by log base 10 of 2. So there is a pattern to be gleaned from this, right? This is exactly the same as this. And so the pattern here is that I'm starting off with log base 2 in this format, but I can rewrite it with log base 10, or for that matter, any base that I want. So I chose base 10 here because that's easy to plug into my calculator. But this base can be, it has nothing to do with the 2, it has nothing to do with the 7. You can choose this base to be whatever you want. And then for the logarithm in the numerator, you keep the same number that you had in the original logarithm, right? So the 7 will stay in the logarithm on top, and then the base of the original logarithm goes inside the logarithm on the bottom. Right? So we get to choose a new base for our logarithms. It can be whatever we want, but then these numbers have to go in these specific positions, right? Whatever was inside the original logarithm goes in the logarithm on top. Whatever the base was of the original logarithm goes in the logarithm on the bottom. And that allows us to switch from any base to any other base. So now if you do get a log base 2, you can always switch it over to log base 10 anytime you need to plug into your calculator by following this pattern, right? So that's all this formula is trying to map out, right? It's the same pattern, right? Whatever's inside the original logarithm, I should probably use a different color here. Whatever's inside the original logarithm goes in the logarithm on top. Whatever the base was of the original logarithm goes in the logarithm on the bottom. And the new base can be whatever you want it to be. So choose something that you find useful. All right, so let's look at an example of using the change of base formula. So here we're given this logarithm, log base 2 of 11. Now some of you will have a calculator that lets you type in the base 2. So this problem is going to be very silly for you because all you have to do is type that directly into your calculator and you'll get your answer and you can move on. But if you're like me and you have a calculator that doesn't allow you to do log base 2, I'm going to have to use the change of base formula, right? And so I need to change this from base 2 to a base that my calculator can actually compute. So I'm going to change it to log base 10. Again, I could change it to whatever I want. I'm going to choose log base 10. Whatever's inside the original logarithm stays in the logarithm on top. So I'll keep the 11 in the logarithm on top. And then whatever the base was of the original logarithm goes in the logarithm on the bottom. Right? So I'm going to plug that into my calculator, divide these two. So I'll get log base 10 of 11 divided by log base 10 of 2. And I end up getting, as an approximate answer, 3.4594 when I round to 4 decimal places, which, like I said, is their favorite thing to do in this section. So, all right, so that is converting a logarithm to a different base so that you can plug it into your calculator to get an approximate value for that logarithm. All right, so that is the end of section 4.3. So the next section that we'll be doing is 4.4. So if you're one of my students, if you have any questions about anything in this video, next time I'm in class, please bring your questions. I'd be happy to answer them, or make an appointment with me or come to my office hours and I'd be happy to help you sometime outside of class.